Good morning, students. Today we are going to discuss the periodic trend in the chemical properties. And to begin with it, we have to first go through the valence or the oxidation state. Now, students, you are very well aware of what is valency, right? Or what is the valence. Now, according to the on the basis of the electronic configuration, we can determine the number of the valence electrons present in an atom, right? And the valence is the combining capacity, or the valency is the combining capacity of that particular element. Now, students, generally we find that when we are moving across the period from group 1, there is increase in the number of the valence electrons. From group 1, in group 1 we have got only 1 electrons in its valence shell. When we move to group 2, we will have 2 electrons in the valence shell. Similarly, when we are moving to group 13, 14, 15, 16, 17 and 18, there will be increase in the number of the valence electrons, and it increases from 3, 4, 5, 6, 7 and 8. Right? Now, students, the valency is going to be the electrons, or the valency is the combining capacity, which we can determine by just checking the valence electrons, right? And from group 13 to group 18, it is the number of the electrons, valence electrons, will get subtracted from 8. Right. So, what is the valence or the oxidation state? Before going to it, we should know what is valence electron. So, valence electron is the number of electrons present in the valence shell, or the outermost shell. Now, students, let us take an example that when we are in group 1, we are taking the element of a group 1, let it be lithium here. We know that its atomic number is equal to 3. Now here, when we write down the electronic configuration, it is in this way. So especially the S block and the P block elements, which are known as the representative elements, right? In these elements, the valence is the number of the electrons present in the outermost shell for group 1 and group 2, and from group 13 till group 18 it is 8 minus number of the valence electrons. Now here this lithium, it belongs to the S block, it has got the valence electron 1, right? So the valence electron here is 1, and its valency is also how much? It is 1 only. Now we will take an example from the group 2. So let it be beryllium. So here Z equals to 4. So when we will write down the configuration, it will be 1s2, 2s2. So here then the valence electron is equal to 1, and students valency is 2. Right. So these two, they're the representative elements and they belongs to the S block. So the S block elements will have the number of the valence electrons will be considered to be the valency, or it will be known as valence, or it will be known as the combining capacity of that particular element. Now when we jump to the P block, let me take an example from group 13, right? So we have got boron. Now Z equals to 5 in that case. So we have got 1s2, 2s2, 2p1. Now students, here the valence electron is 1, 2s2, 2p1. It is 3 here. 2 plus 1, 3. So here simple, the valency or the valence will be 3, right? Boron also belongs to the p block element, right? It belongs to representative elements, p block elements, right? So it has got the valency of 3. Now when we come to carbon, Z equal to 6, so it is 1s2, 2s2, 2p2. Now students, here the number of the valence electron is how much? It is 4. So if the number of the valence electron is 4 here, in that case the valence of an atom, right, it is also here how much? It is 4. Right? Now we will just take an example of, here this was group 13, this was group 14, now group 15. Now we will take the example of nitrogen here. Here Z equals to 7, so it will be 1s2, 2s2, 2p3. You can only write down the valence shell configuration also. So here students, the number of the valence electron, it is how much? 5, right? So the valency or the valence is going to be 8 minus 5, that is how much? It is going to be 3, right? This is for the nitrogen, right? But it's a higher group, the members of the nitrogen group, that means belonging to the group of nitrogen, like phosphorus, arsenic, right? They in their compounds also show the valence of 5. They can extend their valency. Again, I am repeating here that the valence of the nitrogen is 3, right? But the members of this group, that means of the nitrogen group, group 15, right? That includes phosphorus, arsenic, antimony, bismuth. These elements, since they have got the d subshell available with them, right, they have got vacant d, or they have got the d orbitals available, so they can get their valency extended to 5 also, right? Now nitrogen, then comes oxygen, so Z equals to 8, so it is, I'm just writing now here the outermost 2s2, 2p4. Here the number of the valence electron is how much, student? It is 6. 2s2, 2p4. So 2 plus 4 how much? 6. So the student's valency or the valence is going to be how much? Is the valence electron here? It is 6. So it is 8 minus 6. We will get 2. Right? Similarly, the members of the oxygen group, other members of the oxygen group, right? We have got silicon, right? So they can extend their valency, or they will show in their compounds the valency of 6 also. Again the same reason, because they have the availability of the d subshells, so they can extend the valency. So students, if you just go for the halogen, right, that is here, next is fluorine, Z equals to 9, so it is 2s2, 2p how much? It is 5. So the valence electron is how much here, students? It is 7 here. So the valency which it can show is going to be 8 minus 7, that is 1. But there are certain compounds are present where the elements of the halogen group, that is fluorine group, chlorine, bromine, iodine, they show 7 also as its valency, right students? So here we have discussed. So students, here if it is not visible, so it is just here fluorine. In the similar way as I have done here, 2s2 above, we have just written for the fluorine its atomic number, its valence shell electronic configuration, then we will write down the valency of it, valence electron, that is 7, and at the end we are writing the valency, that is 1 comma 7, right? The last line may not be visible to you, but just I'm just telling it again. At the last, I have written fluorine. Then atomic number Z equals to 9 within the bracket. Then it is 2s to 2p5. Its valence electronic configuration. From there, we have written the valence electron which is available with it. That will be 2 plus 5, 7. And then the valency, that is 1. Right? 8 minus 7, 1. And in the elements other than the fluorine, in the group 17 groups, they will show the valence of 7 also. Right, students? So what we are coming to conclude here, that when we are moving across the period, these I have written the member elements of the which period. You can just easily predict. Here there is outermost shell which is being used is 2s, second shell. Right. So these are the elements of the second period. Right. So we have written the elements from atomic number 3 to atomic number 9. That means from group 1 to group 18. Group 1, group 2, then group 13, 14, 15, 16 and 17, and then last is group 18 also. So there, okay, now for in case of group 18 students, we have got completely filled configuration. That means S subshell and P subshell is completely filled up. That means the number of the valence electron in that case is going to be 8 here, right? For example, here if it is neon, right? So if we write for the neon, so what is going to be the electronic configuration of the neon? It will be 1s2, 2s2, 2p6. So outermost shell has been completely filled up. It has got 8 electrons, right, students? So 8 is a valence electron, and if we just get its combining capacity, it will be 8 minus 8, that is going to be 0, right? And if it is its other group members, they can show the valence electrons. Other members means elements other than the neon in the inner, in the noble gas group. They can show the oxidation, sorry, they can show the valence of 8 also, right? So you will find here that when we move across the period, there is increase in the number of valence electrons, right? It is increasing from 1 to 8, right? But the valency, it increases from 1 to 4, and then it starts decreasing, right? And it reaches to 0, right? This is across the period. Now students, when we will move down the group, right, what will be the effect on the valence electrons, or what will be the effect on the valency of the elements? Now students, when we move down the group, right, the number of the valence electrons will remain the same, right? As a result, they will show the same valence. Hope so this is getting clear. When we are moving down the group, right, let it be S block group 1, from lithium, lithium, then sodium, right? So when we are moving down the group, in that case the number of the valence electronic will remain the same, and hence the valency which will be shown by that group is also going to remain same, right? And and the higher valency will be shown where there will be the availability of the d orbitals, or where there will be the availability of the vacant orbitals. There the higher valency will also be shown, right students? So just go through it. We have discussed here the valence electrons and the valency. Now students, we are going to discuss about the oxidation state. Nowadays, the term oxidation state is used frequently. Now, what is the oxidation state? Oxidation state is the charge acquired by the atom of an element on the basis of electronegativity of other atoms in a molecule. That means in a compound, we will have two or more than two atoms can be present, right? Now, in the molecule of that compound, what will be the charge which will be acquired by the atom of an element with respect to the other element on the basis of the electronegativity, right? So here Now we are going to consider the example of the OF2 and Na2O. To just understand the concept of oxidation state, we are considering OF2 and Na2O. We will take it one by one. So first, let us take this example OF2. Now in this compound, students, OF2, right? If we just write down the configuration of oxygen, so what I'm just writing the valence shell. It is 2s2, 2p4. And what is that of fluorine? It is 2s2, 2p5. So you can check the electronic configuration. Here it is just visible that fluorine, it has got the 7 electrons in its outermost shell, whereas in oxygen has got only 6 electrons in its outermost shell. And definitely the nuclear charge, right, of fluorine is going to be very high. So if we just compare the electronegativity of oxygen and fluorine, so fluorine being they having greater nuclear charge with respect to oxygen will have higher electronegativity. So on that basis, right, so here it only needs one electron, but oxygen one atom has a tendency, right, this oxygen here, right, it is 2s2, 2p4. So if it just get its one electron shared with the other, what will happen here? It will get the half filled configuration, and the fluorine will get the stable configuration. So one of the oxygen atom, right, it is just getting its one electron with this fluorine atom, right? So we are getting here how much? For one fluorine atom, sorry, for one oxygen atom, right, we need how much? 4, it's 5 and 6, right? 5 and 6, that means here that we are here for each oxygen atom we will require 2 fluorine atom, so that a a stable molecule is being formed, right students? So if you just check the electronegativity of oxygen and fluorine, I'm repeating again, which one is more electronegative? Definitely it is fluorine, which is more electronegative than oxygen, right? So in the formation of OF2 molecule, each of the two fluorine atom shares one electron with oxygen atom, and oxygen atom shares 2 electrons with fluorine atom, right? So again I'm saying that 2 fluorine atom are going to share 1 electron with oxygen atom, and oxygen atom shares 2 electron with fluorine atom. As a result, since each fluorine atom is sharing only 1 electron, so the fluorine will show the oxidation state of -1, and oxygen will be showing the oxidation state of +2, right? Now just come to the next compound, it is Na2O, right? We know that the configuration of sodium, right? So it is going to be neon, and then we have 3s1, right? This is the configuration of sodium. And in oxygen, we know that oxygen has got the configuration of outermost shell. It is 2s2. We are writing it here as helium condensed form. It is 2p4. Now student, in this compound, that is sodium oxide, if you just check the electronic configuration of neon and that of oxygen, right? So what you will find that for the formation of Na2O, oxygen being more electronegative, you will see now if we compare the electronegativity, sodium and oxygen, oxygen is more electronegative, accepts the electrons, one from each of the two oxygen atom, and thus the oxidation state of oxygen is how much? It is -2. If you students again compare the electronegativity of sodium and oxygen, you will find that the electronegativity of oxygen is more than the sodium, right? So the oxidation state, which is based on the electronegativity, right, of the other atom which is present, so it will be for sodium it is going to be +1, right? Because two of the sodium atom are going to lose its electron to oxygen, and oxygen is going to accept the 2 electron and it will get the charge of -2 on it, right students? Hope so this is clear to you. What is oxidation state? Oxidation state is the charge which will be acquired by the atom, right, on the basis of the electronegativity of the other atom which will be present. If you see here in this case, you can see that oxygen is getting the oxidation state of how much here students? It is +2. But in this case, second example, you can see that it is showing the oxidation state of -2. Right. So why it was here +2? Plus why? Because it was bonded to the more electronegative element there, chlorine, and in this case it is bonded to the electropositive element. So with its respect, it is going to get the negative charge, right? And the one sodium atom is going to lose one electron or will to the oxygen atom. So it is getting, for per atom it is how much? +1, right students? And in this case, you can see that for the fluorine, right, it is for per atom it is going to be how much? It is -1. So this is about the oxidation state, right? Now the S block and the P block, which are the transition elements, they generally they show the valence electrons, okay, valency, right, which is generally 1, and if there is any variation, right, it will be variable. If it is there, maximum it can show 2 or 3. But we have got the transition elements students, D block elements and the F block elements, they show variable oxidation states, also, and variable valency also, right? So that is about the transition elements and the F block elements, right? So whereas the normally the representative elements, they show the valence electrons, valency, which is generally fixed, and if there is any variation is there, it will be only few variable oxidation state will be possible. For example, if we take oxygen, right? So generally oxygen, we have got the valence is 2 here, but sulfur is there which can extend its valency to 4 also and 6, just because of the availability of the d orbitals, right? So this is there about the oxidation state, and student, these oxidation state definitely affects the chemical properties of the elements, right, in a periodic table. So student, just go through it very nicely, that how the oxidation state depends upon the electronegativity of the other element in the molecule.